Okay, what are the possible optimizations? Well, first of all, we already talked about exponential backoff, so that can be a component, but a very simple one is really just to get rid of this barging in, if you wish, the test and set, which is an unconditional right, which generates all this validation and all that side effect. Well, before you do a test and set, do a simple test first. Okay, test, then test and set. It's usually called a test and set. But really it's test, then test and set. So why so? Well, you're loading something into a register, and you find out it's already logged. You simply spin in the loop to say, okay, I'm waiting for this to become 0 before I try test and set. Now what happens? Now if someone owns a lock and other threads come to the same location and trying to enter the critical section, they will each load the lock into their register and spin locally. So one memory transaction. And then you spin locally. You're just looking inside. And any other new thread that arrives will only issue a read, therefore will not disturb anybody. And that's great. The only problem is when the current owner of the lock releases the lock, that's when a write happens. That's going to invalidate everybody, and everybody comes back in, read a copy, possibly all reading the 0, and then possibly all try to test and set. Okay, but that's better. Test, then test and set is far better than just do the simple test and set as we showed. Okay, so we're going to assume that we're going to use that. That's sort of the baseline. Slight improvement on the original code. So now, we've been assuming we have this test and set instruction all along, but you know that, or we know that this is not true. In most commercial processors, actually I shouldn't say most commercial processors, but in the most RISC design variants, they use a pair of instructions. Remember the philosophy of RISC instruction set? We don't want a very big instruction that's hard to implement. We want a couple of them. Micro ops. We want to break down long task into a couple of steps. So the typical implementation uses what's probably called load linked store conditional more often. I think sometimes they have different names in different companies. Maybe load locked is one variation that I've seen. But you call them load linked store conditional, people understand. So what is this thing? What is load locked or load linked? Well, there is a instruction, a register, an implicit register, which is used to remember what address you're loading. Okay, so when you do a simple load linked register 3 from a memory location, let's say X, this implicit register, there's only one of them, so we don't give it a name, would remember this register X. Okay, and why? Why do we remember this address? Then we're going to monitor if anybody else has written to the address X. If not, then that's great. Then if you have a subsequent store conditional, we will allow you to actually store. But if someone else has written to the address in between the load linked and store conditional, then we will notice that by checking this register, the link register, the implicit register. If someone wrote to it, we would know, thanks to coherence. We would say, oops, this is invalid. Okay, you can, I don't know, you can remember this is invalid, no longer useful. And then when we try to do a store conditional, we will check this bit. If it's already invalid, the store conditional would not continue because it's a conditional store. Okay, and then you know that this whole thing is not atomic with respect to another effort, because in between this pair or this group of instructions, at some point in time someone else wrote to it, right? That's the whole point. How is this implemented? Well, if you have a logged register, let's say it's a bus-based system, you monitor what's happening on the address bus, and there is a write to a line that contains address X. You can check this just like your invalidation circuit. You check, you check not only your cache, your write buffer tag, you also check this implicit register. You can call this the link register. You check the link register's content, and if there's a match, you set the bit to invalid. Okay, and if it's a directory-based protocol, maybe by the time you try to issue store conditional, your link register is still fine, and you say, oh, hey, I can do that now. So you do store conditional, which is what? Which is a store. It's just a conditional store that is allowed to happen, and then you send it to the directory, to the home node, which may still reject you, to say, oh, too bad, someone else came ahead of you. So only the winner will proceed. So this is not gonna cause you a problem, okay? So that's what we're gonna assume. Load link store conditional. That's the typical code. But just to make sure that we understand this, how does the code work? So it's going to be something like this: load linked. Let's say R1. Let's say it's address X. Okay, so it could be in the address X is in your register R2. Okay, so you have it. Now let's say, so if we want to do test and set, and let's call that whatever, give it a label. This is label try. Now this is very simple now. Branch if not 0 R1 try. This is your test, right? This is your test, first test. And the next step is your test and set. So your test and set is going to be this, right? This is, if it's not there, if it's not 0, if it's not unlocked, okay, I'm just going to wait. But if it is logged, I'm going to try to write to it, okay? So what you would do is to really load and then store. But we already loaded. We already loaded over here. So all we have to do is to store the result to it. Let's say I already made my R3 being 1. Okay, so now all I have to do is to say store conditional R3 into memory location 0 R2. So store conditional is interesting. It's first going to check the link register. The link register still says it's okay. Then this becomes a store instruction. Okay, store instruction issues. It may not succeed. It may still be nacked by the directory. So the result is going to be, this is a different store. This is a different instruction than regular store. Regular store, you simply take the content and put it into the memory location. This store has two components. First, you try to do that. So that's one, component 1. 2, you're going to update this. What is this? This is the code. This is the success result. So if you're successful, it's a 1. If it's not, it's going to be a 0, or whatever is the detail. So you then check. Let's say in my example, the agreement is 1 indicates success, okay, and 0 indicates failure. Okay, if you failed, then you say if it's 0 that I failed, R3, if R3 is 0, then go back to try. Okay, so that's your test. This is your test and set already. And that's load link store conditional. That's the code, how you write a test and set. But the beauty of load link and store conditional is actually we can do more than just test and set. We can do a lot of these other things. In fact, some processors give you fetch and op. What is a fetch and op? Fetch and increment. This is sometimes what we want to do. We don't want to lock. We simply want to say, you know what, add 1 to the global counter. So that's fetch and, or that's fetch and add, fetch and increment, usually called. But what if it's not fetch and increment? What if it's fetch and decrement? What if it's fetch and multiply by 2? So fetch and do something on it is one type of common use of these atomic operation. Another type is compare and swap. Okay, how do we use this? Well, here is the thing. Suppose this is very common. Suppose we have a whole bunch of working threads. Okay, how do we load balance them? What does that mean? Because if I have a parallel program, I have multiple threads. Each needs to work on some part of the bigger problem. Some problems are easy. I have an array, 2 million elements, and I have 10 threads. Okay, the first one works on the first 200,000, the next works on the next 200,000, and so on and so forth. And they probably will take about the same amount of time. But sometimes this static scheduling, that the work division is prior to the work, it's already scheduled, sometimes this is not possible or not efficient. We don't know how long each element would take. So there is a type of workload where you gather all the pieces of work. You put it in a linked list. Whoever is done with the previous piece of work, come back, get the next assignment. And then there is a global list, and once it's completely depleted, we're done. Okay, so how do you do that? Well, you go and dequeue from the work queue. But then there's a problem, right? The dequeue is a whole bunch of instructions. You have to set the, let's say you have this linked list, right? And so on. So you have a header that points to this. What you want to do is to have a pointer to point to this piece of work, that's yours, you want to dequeue it, and you want to set this to the next guy. Okay, so there are a couple of things you need to do, not just one thing. And you want this to be atomic, because otherwise you may have 2 processors coming in at the same time, all trying to do this, and that's bad. Okay, so you want this to be in a critical section, the dequeue to be in a critical section. But instead of having a lock and go into the critical section to do this amount of work, you can actually, if you have compare and swap, you can actually do what is written down over here. What is this? I have an old header that points to this, so this is your old header, and I have a new header point to the next. So this is the new header. Okay, let's be careful and erase this thing over here. Oops, too big. Okay, let's have new header pointing to this, and then we want the new header to be assigned to H. Okay, so what do? We compare to see if the header, or big H in my drawing, if the header is the same as the old header. If they are the same, is this the same? That means it hasn't been upgraded. Then atomically make it point to that. So that's compare and swap. Okay, That means please compare, and if this is true, swap this with that. So if I have compare and swap operation, then I don't need a critical section. I just need this code and do compare and swap. Okay, how do you do compare and swap in with load link store conditional? So the format would be if let's say R1's content is the same as memory location X, then put R2's content into memory location X. Okay, compare and swap. All right. What do we do? So how do we do load link store conditional? Load link R3 X. We load the value in, and then compare, right? Branch if equal. I'm just making this up. This is not any particular instruction. R3 and R1, if they're equal, then great. Or let's maybe do branch if not equal. That's easier. Okay, branch if not equal R3, then go to fail. Okay, so we're not doing this. So fail would be here. Else, let's say they're the same, and then I store conditional R2 into X. Now I'm done. And this fail you can handle. If it's not true, what do you do, right? How you handle depends on what you want to do. So you see, the beauty of load link and store conditional is that they are creating a critical section. This is a critical section in the sense that whatever we're dealing with depends on the value, in this case memory location X, not being updated by someone else. Again, it's a critical section with respect to another effort on the variable of interest. So we don't need what I loosely refer to as a critical section. What I mean is we don't need to have lock and execute my critical section sequence of instruction and unlock, because the effort to lock or unlock probably will be a couple of instructions with load link and store conditional. We already wrote the piece of code. Remember the test and set code that involves a load linked, involves a store conditional, involves some instructions other than that. Here I use fewer instructions, and I already had my critical sections implemented. Oops. Nope. So that's the beauty of load link store conditional. It creates the beginning and the end of a critical section that you want. Okay? You don't have to use this pair to have a lock. You can. Okay? If your critical section is very long, then probably you should do that. You shouldn't try to wrap around the load link store conditional to wrap around your long string of instruction with load link store conditional. You should use load link store conditional to grab a lock, and then you go into that critical section. Okay, so that's what we're going to assume. We're not going to assume test and set as an instruction. Okay, it's possible you may have a machine that uses test and set, but it's more likely that the machine, or a well-designed one anyways, will use load link store conditional as a very generic and very flexible means of giving you the capability of test and set. So now that's just, what did we do? We did test and set, okay, which is really not that much of a big leap forward. It's sort of like that's what you should have done to begin with, and not the stupid test and simply test and set. And here are the real kind of advanced critical section guarantee lock algorithm. ticket log. You've all been to some sort of location, be it, I don't know, my most recent, my analogy used to be DMV. You go get your driver's license renewed. But more recently, I was taking a blood test, and the place had a ticket dispensing machine. You go in, grab the ticket. When it's your turn, you go in and do it. So that's ticket log. It's the same idea. When you arrive, you get a ticket number. This ticket number is monotonically increasing, of course, so there is no repeat. And then it's a first come, first serve. Okay, so getting the ticket number is really a fetch and increment. You fetch your number, but at the same time you increment this global counter, and that's for the next guy. The next guy's turn is 15, you're 14. Okay? And release is easy. Release is basically whoever wants to say currently serving 12. The release is incrementing that from 12 to 13. So the next one to be served is number 13. And since there is only one thread in the critical section, releasing is just a write to that rather than a fetch and increment. You don't need that. So this ticket log, this concept, is actually ensuring fairness in a sense. Well, first come, first serve. Okay, and you can actually try to. So if you think about it, what happens in the Tessen set? Okay, the problem in terms of invalidation is when the critical section ends, the releasing of the lock is what? It's a write to the lock variable. Okay. What do? We set it to 0 to say it's no longer locked. And suppose many threads are waiting for it. What happens? Then there is an invalidation. Everybody's cache line gets invalidated. The cache line that has this lock, okay, that gets invalidated. And then everybody goes and try to load the new value. And it's the same story here. So let's perhaps explain this. Okay, so I have multiple threads. Okay. What is Tessen set? Tessen set is basically, okay, I do a load. It doesn't have to be a load link, but let's say we use regular load for the first test, and let's call the logs variable x. So load into R1 x. Branch if not 0 R1 lock. So that would be lock, right? And if we're fine, this is a little bit repetitive, I have to load it again. X store conditional R2 into X, and branch if not 0 R2 branch 0, sorry, branch 0. Again, we're assuming 1 is the success code, 0 is the failure code. And we'll go back to lock again. Remember, this is my Tessen set, but this is the lock part. What is unlock? Unlock. Well, that's easy. That's basically store R0. Let's assume that that always contains 0 value. Some instruction said it's R31, but there is usually a dedicated register for 0, and store that to X. That's it. Okay, so suppose I have P1 in the critical section right now, in the critical section. P2 and P3 all wanting to get into the critical section. And what would they do? They would be in here, right? Just looping around, looping around. And thankfully, X is going to be in the cache. So they're just doing this locally without bothering anybody. They're not making any real forward progress, but they're not using any other resource than their own local processor. Now imagine what happens when we have a store. Oh, we go to this guy, invalidate their cache line, right? And then what happens? They will all want to read the new X and possibly have a little bit of fight because they're all going to try, they're all going to read X finding it's 0, and they're all going to try to go through test and set over here with load link store conditional. One of them will succeed, the other would fail. But it's sort of unnecessary. Why? Because what if we just invalidate this guy? Okay, he will reload. He will be the one to get into the critical section. Okay, this is an example of just 2 threads. Sorry, this is P3. Imagine there are lots of threads waiting for it. Invalidating all of them would make all of them come back, and this fight is actually pretty horrible. You know, you can pause the video, do a calculation yourself, assuming we have a bus-based system, and it's a round-robin arbitration. Every guy gets to issue a memory request until someone gets the second one. You try that and do a calculation and see, suppose we have 8 threads waiting, how many bus transitions does it take for someone to get the bus, to get the lock for the next one? So this whole thing, what happens if I have a advanced ticket lock? Okay, the code looks somewhat different. I'm not going to write instructions this time. I'm just going to use pseudocode, okay, to get the idea. So this is what we do. Let's see, my turn. Let's call that my turn is fetch and increment. Oh, I don't know, turn. All right, and while my turn is not, or yeah, sorry, is not serving, I am going to wait. Okay, and if my turn is the serving, then it's my critical section. Next is my critical section. Let's erase all this. And then when I'm done, after I'm done, what do? Serve equals serve plus 1. Okay, so turn is initialized to 0. Whoever comes in first. So at the very beginning, turn is 0, serve is 0. Okay, so the first guy who arrives would set turn to 1. Okay, but his my turn is going to be 0, right? You're going to fetch the current turn and you're going to increment, and then you see what is my turn? 0. Who's currently being served? It's 0. Oh, that's me. I don't need to wait. I go into critical section. But when I'm done, I set the serve to 1. So that's ticket lock. Okay. So now what happens? Let's imagine the number of validations and all that kind of thing. Let's erase this. So this is a variable. Ooh, sorry. turn. Right? So this is a variable, that's a variable, and this is a variable. But my turn is a local variable. Okay, everybody can. It's private variable. It doesn't have to be shared by anybody. Every thread has their own little. It's on the stack, private. So we don't worry about it. And then when you come in, you're just fetch an incrementing turn, and that creates an invalidation for anybody. But that's fine. Everybody just uses it once. It's a miss. You go, you get there, you increment. Not a big problem. And guess what happens on the, and then you're just, this is your local variable, nobody writes to it. The serve is something that gets written once per completion of critical section. Okay, so what happens is, suppose your turn is 4 when you come in, so this is my turn, and serve is 1. Okay. This, if you can tie back to the analogy of the whatever DMV, right? You grab the lock, it's 1, and beep beep beep. Every time someone gets a serve, this you hear the beep, and then you look up, and you're gonna see this changing from 1 to 2 to 3. You're gonna hear a lot of beeps until it becomes 4. And in our multiprocessor system, this is in my cache. It is 1. Then what happens? I'll get an invalidation when it becomes 2. Okay? I'll get an invalidation, invalidates it. I have a miss because this is a spin loop. What do? I go back again. Load. This time it's gonna be 2. And then I'll get an invalidation again until I get to 4. You get that? So, good. Can we do better than that? Well, you can. You can sort of delay the read. So, you know, okay, sorry. You know, you're reading 4. That's your turn, and currently it's serving 1. It takes 3 critical sections, so you can take a walk. Take a walk, idle, do whatever, wait. Guess how long it will take you. Wait that long, and then read again. Then it will work, right? Then you will not have all those invalidations sent to you. You get one invalidation, yes, but then you're not eagerly going out to read the value only to be invalidated a couple of times. So you wait. This is sort of like the exponential back off, but it's not exponential, it's just backing off based on the difference between the ticket obtained and the currently serving number. You wait for that long, okay, and then you do that. You load. Then hopefully you're not reducing, you're not generating unnecessary invalidations and read requests. Okay, so there's problem to that. Okay, if you don't have a busy waiting, it's blocking, meaning you suspend the thread, then you can get into trouble. This kind of lock, this kind of scheduling has a problem, right? So we'll not get into that. Yeah, if the guy who gets his turn, let's say that thread somehow crashed, then the whole system is in trouble. Because everybody now think, okay, it's his turn, must wait for him. He's never going to increment the currently serving number. So you're in trouble. Now, this can get even more improved. How about we're not? So the code that I was writing, I am waiting while my turn is not the same as serve. Okay, so you see in this loop, I'm monitoring this variable. It's one variable, one global variable. And every time this variable gets incremented by 1, I get an invalidation. And when that happens, everybody who's waiting will, if we don't do proportional backoff, will go and read. And those are all, most of them are unnecessary. So the idea of so-called array-based log is this. How about we have an array? Okay, how about we have an array? This is 0, 0, 0, 0, 0. Okay, what does this mean? Let's say this term is, I don't know, number 3, number 4, number 5, and so on. What does this mean? This is the ready signal, okay? Ready. And instead of doing that, you say while, let's say my turn is 5. Then you say while ready, my turn, well, that's not 1. Wait. Okay. And when you're done, and you have your critical section, and after you're done, you simply say ready, my turn +1 set to 1. Do you get the point? Basically, instead of waiting for a number, now everybody waits on a different variable based on the turn. Okay? And the one who's finished will set the next guy. So when I'm done, so when 2 is done, it sets 3 to ready. And when 3 is done, it sets 4 to ready. Now, what's the benefit? We're spreading out. We're not all updating one variable that everybody's monitoring. Each one is monitoring a different variable, which is good. Why? Because then you get exactly one invalidation. Now, that said, there is a big caveat. If you thought about it, good for you. If you really do this on a hardware, in this, and create a, let's say, integer array like that, they're very likely all of these are going to be in the same cache line. So if someone writes to this variable, the entire cache line gets validated. So it's not solving your problem. Okay, so you have to somehow spread them onto different cache lines. So in principle, you can do this. It's called array-based. So in practice, you have to be careful about the detail. Okay. So this is array-based. So now we have some simple test and set. It's better than the stupid just test and set. Now we have array-based. We have the ticket log. We have array-based, which is more improved upon ticket log. How do they compare? And with ticket log, we can have proportional backoff. With test and set, or test and test and set, we can also have proportional backoff. We can, exponential backoff. So we have lots of options. Okay, let's compare them. Okay, the code is very simple. We compare them. This is a micro benchmarks, an experiment done just to get an idea of what we're talking about. It does this. We use a mechanism to obtain log, and then we have a fake critical section just like before. It delays for some amount of cycles. And then we're going to unlock the log, and after that, we're going to delay an amount of time before going back and retry. Okay, so then you can change the parameters C and D and see how things goes. Okay, so for instance, we're going to do C equals 0, D equals 0. So empty, no delay, empty critical section. So boom, boom, boom. Everybody just gets their log and enter into critical section. And we want to know how long does it take for this overhead of obtaining a log and releasing the log. And as the number of processors increases, what happens? Remember, ideally, we have some time, right? This is absolute time, so I don't know how long it will take, but let's say it takes half a microsecond, very small. then ideally, no matter how many threads are doing this, it just takes half a microsecond, whatever. Okay, but then we have all these different options. So maybe let's say the red one. What is that? It's ticket log. Okay, let's use let's go through them. Load link, so-called load link store conditional. This is really just test and test and set, and test and set. Okay, this is the same test and set with exponential backoff. Then the next one, the thin red line is ticket log. The next one is ticket log with proportional. Finally, there's array based. Now, we're going to show you what happens if you have C equals 0 and D equals 0. And we're also going to have a non-trivial C. C is not 0, but D is 0. And then we're going to have C is not 0, and D is also not 0. Okay, we'll have all three cases. Pause the video, take a guess. What do you expect the curve to look like? Not necessarily exact value, okay? So if you think about what we've been talking about, the array-based, what does it try to do? Okay, it tries to make sure that when you come in, you get a location and you wait on that location, and there is no false invalidation to you. You're not gonna have to miss and do something stupid on the bus and then go. So this, in the best case scenario, is going to be flat, right? Because that's the idea. It's not going to be proportional. If you have more thread, so be it. Everybody's waiting on their own thing. So think about that. Is it going up? Is it flat? And if it's flat, is it flatted here or flatted there? Try to take a guess just based on what you already know. Pause the video and think about it. And then when you come back, I'll show you the result. In fact, I'll terminate here so you do get a chance to think.